For power dissipation, you cannot assume, you just have to take into account the circuit configuration. You just cannot assume same components arranged a little bit differently will give you the same results, because they won't. Okay? So that's pretty much where we left off last week. And I'd like you to do a lab on power dissipation, because it's important. Then we'll get into series parallel resistors. And let's see, what are we going to do here? Okay. Yes,
Do you have an extra pen I could use for this class?
an extra,
Pen?
oh yeah.
Please and thank
Do you want a pen or a pencil?
you. Pen is better. Pen. Please.
Do you have a calculator?
Thank you. Yeah, come on.
Oh. Still working? Ready to go through this? No? Can I start?
I just realized I used the wrong formula.
Let's go through this and show you the step-by-step. So we're given a parallel circuit, 2 resistors. And the first question is, we want to find the power that's dissipated in each one. Well, we could combine these resistors and come up with the total resistance, and then use Ohm's law to find the total current, and then go back and use power equals I squared R. But we really don't have to do that, because we have the voltage, and we know that voltage appears across each resistor, and so we can just go right ahead and use this equation, V squared over R, to find the power dissipated in each resistor. In this case, it's 50 squared for the 35K resistor over 30, it's 50 squared over 35K. And that is $71.4 milliwatts. Is that what you're getting? Okay, see that? We'll do the same thing for that other resistor. We have 50 squared over 15K. $166.66 milliwatts. Okay, so we have a smaller resistor that's going to draw more current. More current means more power dissipated. Okay, anybody have any questions on that? Now, on the flip side, I'm asking you to use an equation in the book. So this may have been a little bit trickier, but let's go through it again. For the calculate the total resistance of the 2 resistors in parallel. Okay, so that's step 1. We need to calculate the total resistance. And the formula is this for 2 resistors. And of course, if you only have 2, like I went over last week, we can find a common denominator for this particular formula. And come up with a simplified equation, I think, for just 2 resistors. So if we multiply the second term by R1 over R1 and the first term by R2 over R2, we come up with R1 plus R2 over R1 R2, but that's 1 over RT, okay? So RT is equal to this. R1 R2 plus over R1 plus R2. That's just for 2 resistors. You could do that for, you could find a common denominator for 3 resistors, for 4 resistors if you want, but I guarantee you, you're not going to get a simplified equation. It's going to be a lot more work. So here's the equation. And that, if we use that equation, we get $10.5 kiloohms. Remember what I had said last week. If you have resistors in parallel, the total resistance is always going to be less than the smallest resistance in the group. The smallest resistance here is 15K, so you know when you do your calculations, you're going to get an answer that's less than 15K, and that's a good check. In this case, it's 10.5K, so I kind of think we're on the right track, all right? Right off the bat. So that's the total resistance. And then it says, then use the current divider equation on page 194 of the text to calculate the current through each resistor. So since this is a current divider, and like the resistors in series, they act as voltage dividers, and the extent to which the answer that you'll get for voltage drop for here and here and here is proportional to the size of the resistor. Well, that same sort of thing happens for here with resistors in parallel, except there's a little bit of a twist. More current because you have a smaller resistor here, you're actually going to have more current going through that. Lower resistance, higher current. So it's not as quite as intuitive. So if you had this current here as IR1 and this current here as IR2, you would have this. That would be your starting point for that formula, where this is the source voltage. I think in the book they use IT for total voltage. But we know that total voltage is equal to total current, let's use the T, times the total resistance. So if you make that substitution, you have the current through R1 is equal to the total current times the total resistance divided by R1. Divide by this IT, both sides, and you end up with that formula, what is it, 5.5? Yeah, equation 5.5 in the book. You end up with that. I think they use an X. IX over IT is equal to RT over RX, which would indicate, any resistor that you wanted to put in there. So let's do that. Calculate the current through each resistor. Okay, so we have this formula here. And we know that, let's just pick the 35K. I think we were given the total current, 10 milliamps. And that's equal to the total resistance, which is 10.5K, divided by R1, in this case is 35K. Our K's cancel. And that comes to what? Three milliamps. Okay, that's, by the way, you should write that formula down. Large resistance, we have 10 coming in here, 10 milliamps coming in. And 3 is going through the 35K resistor, which kind of makes sense, high resistance, low current, okay? We could go through that calculation again, start out with the formula, but we also know that Kirchhoff's current law says that the current into a node equals the current out of a node. Here we have 10 milliamps coming in, we have 3 milliamps, actually this should be this way. We have 3 milliamps going through that resistor, so we have to have 7 going through the 15K. We have to. So you don't even need to do the calculation, you can just subtract. But we're going to do the calculation, all right? We'll just do it anyway. So I'm going to start out with this formula again. IR1 over IT is equal to RT over R1. So we have the resistor, this time we're looking at the 15K resistor. We have total current of 10 milliamps. We have a total resistance of 10.5K. This time our resistor is 15K. K's cancel. And we get 7 milliamps. So it works. Now the power, I'm asking for the power dissipated in each resistor. Well, we've got a little bit of overkill. We know just about everything we need to know about this circuit. So you can pick a formula. Let's use power equals V squared over R. So for the 35K resistor, what do we get? 71.4. Didn't I just do that? Oh, no, I didn't do it. I don't know the voltage for this problem. I don't know the voltage, so I definitely need the current equation. We have 3 milliamps here times 35K. Okay, let's see what that does for us. .315 watts for that resistor. this guy here, we have 7 milliamps times 15K. And we get 0.735 watts. Total watts, okay? You just add the two together. So if I'm going to power up that circuit, I need a power supply that's at least, it's over 1 watt, maybe a 2 watt power supply, and then I'm good to go. Okay, anybody have any questions? Now, if you just remember when you have to do a problem, there aren't that many equations that you have to work with. You've got Ohm's law, of course, that has 3 forms, but if you know one, you can derive the other 2. You know, if you know just V equals I times R, you can come up with the other 2 very quickly. You have your power equation. Power equals VI, I squared R, V squared over R. Kirchhoff's laws, which are the starting point for everything. Then you've got these 2 equations for resistance. So if you got these 2 equations, your Ohm's law, your power equations, you can pretty much work your way through just about any problem. That last problem with the current divider, where you're using equation 5, the -5 in the book, a little bit tricky, a little bit off the beaten path. You have to do some thinking to get an answer there, but I didn't do anything other than Ohm's law and whatnot, even with that one. Okay, so that's parallel circuits. Now I want to get into series parallel, and I got to tell you, there's absolutely nothing new here. Our analysis has to be a little bit more involved. We have to think a little bit more about what we're going to do first, but the equations are the same. Okay, so let's do a series parallel circuit, and I'll show you what I mean. And we'll go through step by step on how to proceed on just about any series parallel circuit. Okay, so we have 2 resistors here in parallel, but they are not connected directly to the source because you have this guy here, that 100 ohm resistor between those 2 parallel resistors and the source. This is called a series parallel circuit. So whenever you have something a little bit more complex, a little bit more involved, the first thing that I like to do is simplify the circuit to the fullest extent possible, and then just go from there. So the first thing what I'm going to do is find an equivalent resistance for these two guys in parallel. So in effect, if you were looking at this circuit from this direction, I want to find the resistance that these two resistors in parallel are equivalent to, so that from looking at those resistors from the source, I wouldn't know that you'd have two resistors in parallel. All I would see is the total resistance. And that's the first step in simplification. So here's what I'm going to do. I'm just going to use my resistance formula for resistors in parallel, two resistors, and my equivalent resistance is going to be these two. Let's just say that's R1, that's R2, this is R3. It's going to be R1 times R2 over R1 plus R2. And I know the resistance is going to be something less than 30 ohms because that's my smallest resistance. And I get 21.81 ohms for just those two resistors. Okay, so let's redraw that circuit. Step one for simplification. Okay? So those two circuits, in terms of our analysis thus far, are equivalent. So if you could put these two resistors, let's say, inside of a box, with two wires coming out, and you wanted to measure the total resistance of those two wires, and you come up with 21.81 ohms, you wouldn't be able to tell that you had two resistors in parallel versus one resistor with that value. You wouldn't know. It would be impossible to tell. So we've got step one in our simplification. Step two is to just add these two resistors. Now they're in series. The equivalent resistance and R3, the 100 ohm, are now in series. So the total resistance of those guys is just the sum of the two, which would be 121.81 ohms. So that's the total resistance. So now our circuit becomes this. Okay? I'm going to simplify it all the way down to as far as I can go. Then I'm going to reverse the process and make it, and I'm going to go back the other direction. Now, once we have our circuit down to this, now I can find the current, the total current, using Ohm's law. And I get 82.1 milliamps. Is that right here? 82.1 milliamps. Okay? Any questions so far? I could find the power dissipation in RT, but I don't know what that would do for us. So, now I'm going to take this answer here, 82.1 milliamps, since that's the total current coming out of that battery. I can use that same current in this side, in this circuit right here. All right, because the current is the same in a series circuit. So if I know that the current is 82.1 milliamps, now I have a series circuit. I can find the voltage drop across that equivalent resistor, and I can find the total voltage drop across the 100 ohm resistor. And when I add those two together, I should have 10 volts. Let's see what happens. So voltage across the equivalent is equal to what? 82.1 is equal to I times R. Times, what's the equivalent? 21.81 ohms. Is 1.79 volts. Let's do the same thing across for R3. This is equal to 8.21 volts, okay? Okay, 8.21 volts. So I have 8.21 volts here. Volts and 1.79 there. So we have a total voltage is that 10? 9, 10. Okay, so that's a good cross check. All right. since the series resistor, if we go back to our original circuit, that really doesn't change. We didn't change anything there. So we have a voltage drop of 8.21 volts here across that resistor. And that means that the voltage here, that voltage across that resistor and that resistor, has to be 1.79 volts, which is what's left.
And he really doesn't need that, like all he needs.
Got that? Does that make sense or not?
Can you repeat it one more time? Just that middle part you said?
Yeah, what I did was, I started here, came up with the total resistance. I used that to find the total current. The total current, I used the total current to find the voltage drop across this guy, because this is two resistors in series. So I have Kirchhoff's voltage law, which says the total voltage is equal to the voltage drop across each component, so that's R3 plus REQ in this case. All right? 8.21 volts, 1.79 volts. So from that circuit, I'm going back to the original circuit. I have 8.2 volts dropped across here. That means across these combined resistors, and since they're in parallel, I have the same voltage across each one. That voltage across each one is 1.79 volts. And literally every problem that I do, you start out with the original problem, you simplify, you find out what you can on the most simple circuit that you have, and then you go back the other direction and fill in the blanks as you go. That's the technique. Well, look, now that I know the voltage across these two resistors, now I can find the current. So the current through R1 is equal to V over R, R1, which is equal to 1.79 volts, right, over 30 ohms. And that equals .66 milliamps. And the current through that 80 ohm resistor, R2, is equal to V over R2, or 1.79 volts over 80 ohms. Now what does that equal? .375 milliamps. So hopefully when I add those guys, I get 82.5 milliamps. So the total current, this guy plus this guy, is 59.66 plus 22.375 milliamps, which is 82.5 milliamps. Okay, so that's not quite what we found over here. We got 82.1. It's a little bit off, but that's just my calculator. So it's pretty close. 82, actually this was 82.05. Just make sure. Yeah, 82.05. So I've been rounding off a little bit, and that's what I came up with, but it's pretty close. All right, so that's it. I mean, what have I done? I really haven't used anything other than Ohm's law and Kirchhoff's voltage law, the current law. And the key, again, you simplify the equations till you get down as simple as you can, find out the missing components, and then work your way back one step at a time, adding the missing information. Wow. What a mess. Okay, let's see if we can go through this with a lab. I mean, you could look at this all day long and say, yeah, I know what I'm doing, but what you really have to do it to reinforce the whole process. So let's do items. This is the first part is a calculation. The second part is building a circuit, building the circuit using multi-sim, and then the third one is building the circuit with your analog kit. Let's not do that for now. I want to see how long the first two take, and then we'll go from there. So here we go. Resistors in series parallel. Have a go at it. Russell, do you need I have an extra one.
Sure, I'll use it. Use anything.
You know how to use this?